So high or what? Oh. It's really hard. Where's the packet? No.
Oh, sorry.
No, she's still working, but she does it like like first break it. I want to be able to take care of her eyes. She's like.
Hey guys, if you can pick up a packet.
Yeah. Like it's. Yeah. Yeah. It's like that. Oh, yeah. I know, I agree. I was thinking, I thought of really for the today this morning, like before the better not work for it. Wow. No, it's regarding. Because like it was a lot of time. I know I'm
I can't see my integrate.
Oh, yeah.
Bro, the interval system was like, yeah, it was gonna be like, it's not studying. I saw it, you're right, yeah. People, I didn't, but I saw her log line against choice. And like. I felt like that best and I got scared. Yeah. Give I used to get to like, I used to get like. Oh, really? Yeah. No.
What do you think of this? I got to
Gonna cause it. There was like one that was like. And like, I don't even realize companies, so it's fine. I didn't feel. I see it a lot. That's all I really don't know about that. Oh, was it? I was like, no, I did policy. Improve like from both. Yeah. I know. And I'm really like.
Oh, you did do that. Okay. Yeah. Yeah, no problem.
Okay, if we can turn to page 3, and you need your calculator for this.
We'll give my back. You want this too? I said it was over this. And it rolls. Wait, that makes. No, that's funny. Oh god, I thought you said like totally suicide, like and then I saw a story and I was like, you went down there. Yeah. It's like a small refund. Did he like give it to like all of her? He like is going.
Yeah. Yeah, I wasn't. Hey, I was actually scored. I got a reason to score. Yeah. Actually, I'm I need it.
This bold, no one's going to have it, like, that's real nice. I think it's lovely. I love it. Right, where's your comfort? You open it? Oh, this week. I know. And I want it's like, it's like, wait, do it. Wait, you want? I'm laughing. That is pretty good. I have done it usually like someone I don't know. Now I'm in. No, one or I know. I feel like he's having a run, right? Like, actually, other boards. Yes. Did you ask for it? No, I looked at him and I'm like, oh my god. No, but I look at, no, but I say, yeah, what do you?
It's 2:30.
It's so red.
Okay, so we're going to practice the area rules that we learned Thursday. So again, for area, we have to, if we want to do a top minus bottom function relationship, then everything has to be in terms of x. And our equation that we're going to be working with will be in terms of y equals. If you see y equals, that means you know you're dealing with a function. That means that it is in a proper form for our top minus bottom function. But if all the equations that we're working with are in the form of x equals, then that indicates to us that we're dealing with the right minus left. Everything is in terms of y. Our bounds is also in terms of y. So for each of these areas here, I want us to practice with finding the area using top minus bottom, and then we'll switch over to practice finding right minus left. We should get the same answer, but two different orientations. But it's important that that we know how to go back and forth between them. Or if a problem is forcing you into one scenario, that you know how to get into that scenario. So we're going to focus on finding the area of S, region S. So I'm going to just lightly shade in region S. And we're going to work on finding the area of region S. Okay, so first we're going to do top minus bottom, which will be the easier method. Everything is in terms of the function that we're already working with. So, but we do need to sketch the graph because we do need to figure out our boundary here because we're essentially adding infinitely thin rectangles that's going to extend from this boundary all the way to this boundary. So let's go ahead and graph both of these functions. Thank you. Okay, so under y1, maybe y1, you can plug in the 2 minus x cubed function. And under y2, I'm going to have it hold that y equals tangent of x. Make sure that you are in radian mode. If you go to mode, we should be in radian mode. Go ahead and hit graph. Or sorry, do zoom 6. Zoom 6 will get you that standard window. Now, if you look, this is way too much screen for our graph. We only want that little region here in the first quadrant. So what we're gonna do is we're gonna draw a box around this region and then just let the graph zoom in on that region. So if you do zoom box. Okay, so what we're gonna do is when you hit zoom box, there'll be a blinking cursor, and then you're gonna move that blinking cursor to where you want the upper corner of your box to be. Hit enter, and then you can start drawing your box. And then once the box is formed, then hit enter again, and then it will zoom in on that region. But it's when you hit zoom 1, you're going to have a blinking cursor, and your first goal is try to move that blinking cursor to where you want the upper corner of your box to be. So it doesn't have to be exact, but just somewhere where you feel like you can clearly get that region inside a box. So upper left corner of my of where I want to zoom in, hit enter, and then you're gonna draw a box. Okay, don't hit enter again until you see the full box in front of you. So use your arrow button to draw the box. And then once you have the box in front of you, then hit enter a second time, and then it'll zoom in on just that region for you. So now, what's important to us is that order pair. We want to figure out that intersection between those two graphs here. So if you do second trace, intersect, so second trace, intersect. And then you're going to identify to the calculator what two graphs that you want to find intersection for. But you don't want to put your cursor directly on the intersection. Just find the place close to it. So here I have a point on one of the a blinking cursor on one of the graphs, hit enter, and then it'll toggle to the other graph, hit enter again, and then it'll say guess question mark, hit enter a third time, and it's going to find that intersection for you. Okay. Right now, we only need the X value, but eventually we're going to need the Y value as well. So go ahead and put the order pair for that point, since we're going to need both of them later. So 0.902 and then 1.266. So let me draw one representative rectangle that we're going to be using to kind of help us identify the top and bottom graph. And then we're going to put it into this formula here. Okay, so our area is the depth integral from our left bound, which is 0, to our right bound, which is 0.902. But notice everything that we're doing is in terms of X. Our bounds is also in terms of X. And we're adding infinitely thin vertical rectangles with a top graph of 2 minus x cubed. And then the bottom graph is the y equals tangent of x. So now we're going to make the calculator find the area for us. This formula is going to accumulate all the different heights together, add them all together, add up all the areas of all these rectangles that extend from 0 to 0.902. So now do math 9. Now the advantage is that we already have our top function and bottom function stored inside our y1, y2. I mean, right now it's not a big deal. If you want to type everything in, you can. But later on, when your functions get more and more complicated, it's nice to just be able to have it stored and not have to type in the function every single time you want to use it. So from 0 to 0.902. Right now, my top graph is stored under y1. So if you do alpha trace y1, if you're using one of the older calculators, you'll do bars, y bars, function y1, and that will get you to your stored 2 minus x cubed. Alpha trace y2. Okay, so my area is 1.161. Okay, so notice that all these equations are in the form that we want for top minus bottom. Our bounds is in terms of x. Each of our graphs have the form of y equals, because the y equals indicates that whatever is on the right side is ready for us to plug in, and they're all going to be in terms of x, right? So everything that we see is in terms of x, our bounds in terms of x, our expressions in terms of x. What's more challenging is when we're forced into a right minus left situation where everything is going to have to be adjusted. Our bounds have to be in terms of y, and our equations have to be in terms of y. And to ensure that the equations are in the right form, they're going to have, it's going to be in the form of x equals. So if you see that x equals, then you know whatever to the right of that equal sign is going to be a good expression for us to use for that right minus left in terms of y. So now we're going to attempt finding the area of region S using right minus left. But if we do that, we're essentially adding infinitely thin horizontal rectangles, and we're stacking them from the lowest region to the highest region. But the issue is that if we do right minus left, are we going to have a consistent right graph all the way through this region, right? We're not, right? So there's going to be a change. This curve on the right side is going to change to a different curve once we reach above this intersection. So we basically have to think of this as two separate regions, and we're going to have to think about the y values in each of these subintervals. But the first thing to do is we have to make sure that our equations are in the right form, because right now these are in the form of top minus bottom. These are not in the form of right minus left. So we have to write these equations and solve in terms of x. So to solve for x, I have to move that inverse tangent or tangent over, make it inverse tangent. So I'm going to say x is equal to inverse tangent of y. So I want to indicate that this graph is referring to this portion here. Meanwhile, the 2 minus x cubed, we have to rewrite that, solve for a different variable. So if I want to solve for x, I get x cubed is equal to 2 minus y. Solve for x, take the cube root, x equals cube root of 2 minus y. So now this is in the form x equals. X equals indicates that the right side is ready for a right minus left relationship. So this form is going to be tackling that upper portion there. Now, this y-axis is the left boundary. This is also an equation. What's the equation of this y-axis? X equals 0. So notice that they all have that form that we want, right? X equals, x equals, x equals. That indicates that these are all good for a right minus left relationship. Right. Now, our bounds is going to extend from 0 to 1.266. I'll write down the order pair, but we're going to use the y value for our boundary. Everything's in terms of y. And then this here, this is also a y value. Now, this is part of my 2 minus x cubed equation. And if I want to find the y-intercept, I can just plug 0 in for x. So y is simply equal to 2. So this is an upper bound of y is equal to 2. Or the order pair is 0, 2 at this point. So we need two separate equations, right? One that is going to extend from 0 to that dotted line, and the second area that's going to extend from dotted line to that upper bound. So now, if this was an AP exam, I mean, we're all going to go through this method, right? There's no need to go through a right minus left, but we're practicing this right minus left method because down the road, when we're dealing with volume formulas, sometimes we're forced into a right minus left. And the earlier we can get comfortable with the process here, it'll allow us to adjust accordingly if we need L minus bottom or right minus left. Okay, so we need two area formulas or two separate integrals. So one that is going to extend from 0 to 1.266. And then we all do right minus left. So the right endpoint is sitting on the inverse tangent. And the left endpoint of my bottom rectangle is sitting on the 0. And then the second integral from 1.266 to 2, right? We're stacking horizontal rectangles from this lower dotted line to that upper bound. And then we do right minus left. So the right endpoint of my rectangle is sitting on the cube root of 2 minus y. Minus left, the left endpoint is sitting on 0, so minus 0 dy. So I'm going to practice. We're going to plug this into the calculator. Now, on paper, you're using y, but in your calculator, you're always going to use what? X. Yeah. So on paper, the y is the correct variable, but your calculator, don't try to force a different variable in the calculator. It'll complain or it'll give you an answer that you're not looking for. So we'll do math 9. We'll do it twice. So from 0 to 1.266, inverse tangent, I'll use x here. Oops, sorry. I'm going to drop that 0 there. There's no need for that 0. Okay, plus, and then I'll do this integral here, math 9. 1.266 to 2. Cube root, so do math 4. And then 2 minus y, 2 minus x, sorry. dx. Okay, we should get the same answer, 1.161. The hard part is rewriting these equations in the proper form and recognizing that, oh, I can't use 2 minus x cubed and y equals tangent of x if we want to do a right minus left relationship. Okay, is anyone having trouble with calculator? Okay, if you are, I can work with you after class if you're having trouble with any of the keystrokes. So the nice thing is that everything that we need, we've already built. So then when we want to find region R, I think we can reuse a lot of information that we've already done. Okay. So let's go to region R, and let's do a top minus bottom relationship, or finding area using top minus bottom for region R. Let's go ahead and shade in that region. And then we'll do region R using right minus left. So I want you to see this here. We're stacking vertical rectangles from one boundary to the other. So if I have one representative rectangle here, and if I imagine that I have infinitely thin rectangles, is the top of my rectangle always hitting the same graph? It's not, right? Because to the left of this intersection is hitting the tangent of x, but to the right of the intersection is hitting the 2 minus x cubed. So I'm going to need two separate integrals because I have two different top functions over my region here. So let me just highlight what I want to use. Tangent of x for this first portion, and then 2 minus x cubed for the second portion here. But my bottom function is always going to be the x-axis, which is y equals 0. and y equals 0 is in the form that we want. If we want to do top minus bottom, every equation that we're using has to be in the form of y equals, y equals, y equals. So this is indicating that these are proper forms that we need if we want to put it into the top minus bottom function. Okay, so we know the left boundary is 0 here. We have the intersection 0.902. That's where we're going to use that as a middle point. And then we're going to need to figure out what this x-intercept is for that 2 minus x cubed. So you can set this equal to 0, or you can graph it in your calculator and then look for your x-intercept. But basically, you can just solve this by hand as well. Replace y with 0, solve for x. We get x equals cube root of 2. So that can be our right boundary for our second area integral. So area, splitting up into two integrals here. So from 0 to 0.902, we're under the tangent graph. So top minus bottom, tangent of x minus 0. Again, you don't need to have that 0 there. I just want to put that there to indicate that we are identifying our top and bottom function, that we are going through our area formula. And then integral from 0.902 to cube root of 2. And then top minus bottom, the top is 2 minus x cubed, and the bottom is 0. Okay, so plug those in. Right now I have tangent of x stored under y2. I have 2 minus x cubed stored under y1. So I'm going to use y2 and y1, but if you want to type it in, you can. It's not that much of a time saver right now, since these functions are small enough where you can just type it in without causing issue with, it won't take that much longer. Okay, so region R is an area of 0.729. Two-dimensional units. Yeah, technically. If they don't ask you for units, you don't have to provide it, but I just wanted to put unit squared, just for reminding ourselves that this is an area calculation. Later on, we'll be dealing with volume, and that will be a units cubed. All right, next part. Let's do a right minus left relationship for region R. But if we want to do right minus left, do we need two integrals here? Yeah, this one is consistent, right? No matter where we shift that horizontal rectangle, the right endpoint is always sitting on the same curve, and the left endpoint is always sitting on the same curve. So all we need is one integral. However, we need to make adjustments, right? The tangent x, 2 minus x cubed, is not in the proper form for right minus left, but we can just bring down the equations that we've already built, and then we can also bring back our ordered pair that we can reuse. So my adjusted equation for that tangent is x equals inverse tangent of y. And my adjusted cube root of 2 minus, my adjusted 2 minus x cubed is x equals cube root of 2 minus y. But all we need is one integral, since we don't have a split relationship. There's no change in relationship for our right curve and left curve. So our area It's a depth integral from lowest y value to highest y value. Our lowest y value is 0. Our highest y value of the shaded region is 1.266. And then we do right minus left. Right is cube root of 2 minus y, and left is inverse tangent of y. Enter in your calculator. Again, use X's for all your entries. Do not try to force a Y into your calculator. Math 4. Okay. How do we feel about going back and forth between top minus bottom, right minus left? Is that making sense? Okay. I'll say this. This is the hardest part of this unit right here. Students struggle with top minus bottom, right minus left, adjusting to that change, rewriting that equation. That's the hardest part of this unit because everything that we're doing from now on, we're just, I mean, we have an adjusted formula for volume, but it's just a formula. And, you know, building these rectangles and having them in the correct orientation, I think this is the hardest part. So if you feel good about this, the rest of the unit will be, I mean, we're just redoing the same process, just expanding the formula a little bit. But I think this is the most challenging part that students experience. Okay. And that's why I wanted to spend the time to go back and forth between two different forms and have us practice that. Okay. Okay. Now that we have area, we've introduced area. I want to kind of start into the next section, which is volume. Now, volume, we have three different sections for volume, but we're going to start with the easier form. But this relationship is largely going to still be intact that we're going to be using. Okay, so let's go to page 9. So I want to recall finding area under a curve and then connect that with what we're going to be doing in terms of, you know, how does volume come into play for our problem. So if we would call area, let's say we have a curve y equals root x. And let's say we're asked to find the area between these two regions, or this boundary region here between 0 and 4. And let's say we're using vertical rectangles. Right, and all this is review, but I do want to have this as our basis for our volume formula. So area is the integral from 0 to 4, and then top minus bottom, right? So top is root x, bottom is 0 dx. Now, this we can work it out by hand. We know this is x to the 1/2. Okay, evaluate between 0 and 4. It'll end up being 16 over 3. Okay, so that's just some area of this region, right? But what's more important is I just want to point out what we've achieved what we've achieved is that the root x minus 0, this is representing the height component of these individual infinitely thin rectangles that we're building. And the dx is representative of the infinitely thin width of each of these rectangles, right? So I want to see that, oh, there's a two-dimensional component to my area here. I have my width, I have my height, and then that accumulation of area is what gets me to my unit squared. All right, so I want to have this as a basis for when we talk about volume in a second. So essentially, integral notation allows us to add infinitely thin numbers of differently sized rectangles, right? Every root x at a different y value is going to have a different height to form these area calculations. Now, with this method, what we're going to do is we're going to take a two-dimensional shaded region. Let's say it's this one here. And we're going to be rotating this around the axis, rotating it 360 degrees around the x-axis. Now, what shapes do you see if we were to separate all the resulting objects into thin slices? So imagine we rotated this and we separate them into thin slices. What do you see here? These are what? Yeah, these are circular discs. So now, instead of thinking of it in terms of adding infinitely thin rectangles to achieve area, we're going to be adding infinitely thin circular discs to form the volume of some object. But we're going to create our information very much the same way. We're going to take a shaded region, much like how we approach an area region. We're going to identify the axis of revolution. That's going to be the center at which we're rotating our object. So in this case, we call this the axis of revolution. And the problem will always tell you where the shaded region is rotating about. So in this case, we're rotating about the x-axis, which is y equals 0. And if we rotate it, we can begin to see and imagine that there's going to be a three-dimensional object that's going to come out of it. Okay. Now, the distance between that dotted line and the boundary, we're still going to draw this, this rectangle, but now it's not going to be a rectangle that represents the height of a region. This is now representing the what of the shaded of this object, the radius. Yeah. So we're still going to draw the same shape, but now it's going to represent the radius instead of a height of a rectangle, radius of a disk instead of a height of a rectangle. So radius. Or we're going to call this R of x. Okay. So let me just take one circular disk out and just focus on that portion. So we know that this distance is called R of x. That's going to be the radius radius of one infinitely thin circular disk. We know every circular disk will be a different shape, just like how we have all these different shaped rectangles, but they're all taken care of by that function there. So what's the area of a circle? Because we know this is a circular disk, right? Yeah, area is pi r squared. So we're going to adapt that into our area formula, our area of a circle, which is pi big R of x squared. So already this is how many dimensions here? This is what? Area is 2 dimensions, right? But it's going to add a third dimension, and that's with that dx there. So volume will look like this. Integral of pi R of x squared, right? That's the area component. That's already 2-dimensional. But then we add that dx component that will give us the width of these infinitely thin circular disks. and that will give it that third dimension that we're looking for. Okay, so pi r squared is area. Area times another dimension will give us that third dimension. Here, there's only two dimensions because it's height and width. So that's why it's only unit squared. This one, after we go through that pi r squared and that dx, it'll be units cubed. Okay, so if we're ever drawing a vertical radius, if our radius is visually vertical, then it'll be a top minus bottom relationship, just like how we're building our area formulas. But if our axis of revolution is vertical and is forcing us to draw a horizontal radius, then we're going to have to adjust all of our equations. Every equation is in terms of x equals, in terms of y, and then our bounds is also in terms of y. We'll do the easier top minus bottom first. So this is what a problem could look like. Example 1. Find the volume of the solid formed by rotating the curve y equals root x around the x-axis between 0 and 4. So we're basically doing this problem here. We're finding the area volume of this object specifically now that we've kind of gone through an overview. Okay, so the first thing is go ahead and build your shaded region. Just like how you would if you're finding area, you're essentially going to start off very similar to how you do area. We do have an axis of revolution. So you're always going to be, I told, where that rotation is going to happen. And also, you never have to draw the three-dimensional object. Okay, all you need to do is to get enough information from this shaded region and put into the formula, and that's it. You don't have to worry about drawing anything that's three-dimensional. But it's helpful to put that dotted line. So I want us to keep remembering that this dotted line is not the edge of the diagram. This is the center of the diagram. I know because we're not seeing the other half. The other half is going to be down here, right? We're only seeing half the object because this is the axis and that it's going to rotate around that axis. Okay, so I want to keep reminding us that this is not the edge. This is the center of the diagram. All right, so now to build your radius, you're going to put your pen or pencil on the dotted line, and then you're going to extend to the furthest boundary. And it's going to force you to draw a vertical radius, right? And if you're forced to draw a vertical radius, that means you're going to do a top minus bottom for your formula. If you're doing top minus bottom, then everything will be easier because your equations are going to already be in the form that you want, and your bounds are usually going to be easier for you to find as well. So we're just going to follow this formula, but let's build our radius, big R of x. Build your radius the same way that you would build the height of a rectangle. We just do top minus bottom. Right? So top of my radius is sitting on the root x. The bottom of my radius is sitting on the y equals 0. They're both in the form of y equals. They're both properly set up for me to do top minus bottom. So root x minus 0, or just root x. Okay, we're ready to plug into our volume formula. So we do v is equal to, now what I like to do is I like to put that pi out in front of the integral because it's just a coefficient. It's not going to impact my formula. And I want to talk about what to do with that pi. Usually we're not going to plug that in the calculator. We're going to try to have the ability, the flexibility of maybe presenting an exact answer. And if we plug the pi in the calculator, typically that will make it into an approximation. So we do big radius squared. So here's my radius, pi r squared. There's the area component of my circle. Dx, we'll give it that third dimension. And then integral from my left bound to right bound. So how far left is my shaded region? X equals 0 all the way to x equals 4. Yeah, so we go from 0 to 4. Now, eventually, your radius will get larger and larger and messier and messier. So I think it's just a good habit. I mean, right now, you don't have to do it because it's such a small expression. But what I like to do is I like to store my radius under y1. So I'm going to have root x. And then do math 9. Leave pi out of your calculator. So go from 0 to 4. And then alpha trace y1. No need to put parentheses, just do squared. And it'll just naturally square everything inside your radius. And then dx. Sometimes this forces you into a fractional, a decimal value. If it does, you can do math 1 to see if it'll convert to a value for you. If it does, then you can hold it and then add pi at the end. So in this case, it's already a whole number, so there's no change that we need to make. So 8 pi is our volume, and then units cubed. So we're not seeing the full shape. We're not ever drawing the object that we're finding the volume for, but it essentially looks something like this. It'll just be a bowl-shaped object that's completely filled in. Okay, let's practice a bit more with this method. So next page. All right, example 2, find the volume of the object created by f of x equals 2 minus x squared, and there's another boundary I'm forgetting about, and y equals 1. So we're going to be creating a boundary between those two graphs, but we're going to be revolving around the line y equals 1. So let's draw the graph. Well, 2 minus x squared, you can use your calculator, but it's basically a parabola with a y-intercept at 2. And y equals 1. So that's the second boundary that I forgot to put into the instructions here. So there's y equals 1. Then go ahead and shade in that enclosed region. And so we're going to take that shaded region. We're going to rotate it around the line y equals 1. So y equals 1, this is your axis of revolution. I'm going to abbreviate as AOR. And then put a dotted line right at y equals 1 to indicate that we're taking that shaded region and we're rotating it around that dotted line. It's going to end up looking like an egg-shaped object, but really it's not that important that we visualize. We just have to see that, okay, this is rotation. This is going to be this method. Okay, there's going to be a volume that we're going to achieve out of it. All right. This problem, however, does not provide us the boundaries. We have to look for it ourselves. So we're looking for the intersection between these two graphs. And these will be our bounds that we're looking for, x sub 1 and x sub 2. So I can just simply set the two equations equal to each other. I think right now it's easy enough for us to solve by hand, but if it's not easily solved by hand, then you would plug both into your calculator and look for the intersections at each of these points. But we're looking for the intersection between 1 and 2 minus x squared. So x squared is equal to 1, x is equals to plus or minus 1. So -1 and +1 are the boundaries of my shaded region. Okay, next up, draw your radius. Your radius will always extend from your dotted line to the boundary. It doesn't matter where you draw your radius, but just all you need is one representative radius so that you can help identify the top and bottom of that radius. So my radius r of x, I'm forced into a vertical rectangle, and your vertical radius, and your radius is always going to be perpendicular to your axis. So if your axis is horizontal, your radius has to be vertical. Okay, so they're always going to form a T with each other, the radius and the dotted line. Okay, so top minus bottom, the top of my radius is sitting on the 2 minus x squared. The bottom of my radius is sitting on the 1. So there's my radius. I can clean this up a little bit, make it 1 minus x squared. Now, I think we're ready for our formula. Everything we need is in front of us. We have our lower bound, sorry, our left bound or right bound. We have our radius. And the rest is just calculator entry. I'm going to have y1 store my 1 minus x squared. Math 9 from -1 to 1. I'm leaving pi out of the calculator. Now for trace y1 is holding my radius, my new radius, and then do squared, and then dx. If I do math fraction, it's able to convert to a fraction for me. And then I can just say volume is 16 over 15 pi units cubed. And that pi will always be there because we're always going to be area of a circle related. And we're essentially adding infinitely thin circular disks. And that circular disk has that pi in our formula for area. Okay, real quick here. Let me see if I can just do one instance of example 3. We're taking our shaded region, and we're going to be rotating about the y-axis. So here's our y-axis. So now we're rotating around a vertical line, which is going to make my radius come out what? Horizontally. It's always going to form a T with your dotted line. And if you see a horizontal radius, we have to make an adjustment, right? Everything that we're doing has to be in the form of what x equals. Our expression has to be in terms of y. Our bounds is also in terms of y. So anytime you see a horizontal radius, just know that there's some additional work ahead of you. The equations are largely not going to be ready for you to use. But this one is easy enough for us to rewrite. This is good for top minus bottom, but not good for right minus left. Solve for x. X equals 1 minus y. So x equals 1 minus y represents the diagonal line. And what's the y-axis here? What's the equation? X equals 0. So these are both in the proper form for us to use our right minus left. And our volume formula will be from lowest boundary to highest boundary in terms of y. So 0 to 1. Pi out in front. Builds your radius. Your radius is right minus left. So 1 minus y minus 0. Right endpoint of my radius is sitting on the diagonal line. The left endpoint is sitting on the 0. And then just put your radius inside a square. Pi radius squared. In your calculator, you're going to use x, but on paper, you're going to write y. And it's going to come out to be 1/3. And then add pi units cubed. Okay, your homework is just page 11. I'll send out a reminder this afternoon.
For weeks. Yeah. No. Well, it's like one of my last. It does scale. Yeah, I know. Yours stays on way longer than mine.
I live alternative. I drew the thing.
Oh, yeah, yeah. No, I like, I like redhead.
You guys love Thursday.
It is so synthetic that you think. No, it's not my fault.
Thanks, guys. Have a great day.
I got both my kids, guys, and after. I was like, what?